Very nice that you came today, and let's get to hypoxia, a crucial theme, crucial question for exam. Okay, so hypoxia. And what is the flight plan for today? First, we're going to go through some terms which are very much important in pneumology, etc. Okay, so terms, some special terms. Then we're going to go through different types of hypoxia. That's very important. There are 4 types, so I'm going to mention 4. We're going to do sort of a table, so types of hypoxia. And then we're going to go in more detail. I'm going to we're going to talk about anemia, okay, and hypoxia mainly. Hypoxia. And there's a term we're going to definitely define and talk about it. It's cyanosis. That's very important, cyanosis. Let's say the last one I'm going to mention, but I'm going to mention it during the talk. It's going to appear there, these words there. Let's say redundant in this lecture, and that's going to be ventilation perfusion match versus mismatch. Okay? Good. So, first of all, terms. And basically, there are many terms we could say, but I would like you to know, first of all, what is hypoxia. So, can you tell me what is hypoxia? That means decreased partial pressure of oxygen in the tissue, as we talk. So decreased PO2 in tissues. Okay. Then what is hypoxemia? Hypoxemia, that is decreased partial pressure of oxygen in arteries, in blood, in arterial blood. Okay. And then we have hypocapnia. Hypocapnia, that talks about CO2, partial pressure of CO2, again, in arterial blood. So very important term, hypocapnia. Decreased partial pressure of CO2 in blood. Okay. And basically there's another term, anoxia, but we don't use that too much. It means, anoxia means it's no oxygen in the blood. And again, your beloved term, ischemia, that means not only that in the tissue there's not enough of oxygen, so there's hypoxia, plus not enough of nutrients, so decreased O2 plus decreased nutrients and everything, plus increased waste products. Okay? Yeah? So that's ischemia due to decreased perfusion. And then there's term which you might not know. That's asphyxia. And asphyxia, and to be honest, I was also surprised in my later studies that actually the term, if you translate it from Greek, it means something else. Asphyxia means no pulse if you translate it like correctly. But forget that, okay? It was especially used in connection with dead newborns, and they had no pulse. Okay, and somehow like there was evolution of this term, and nowadays if you say asphyxia, it talks about breathing actually. Okay, so remember, it means decreased O2 in the blood plus increased CO2. Okay, so asphyxia is connected with strangulation. Okay, and typically, so it could be newborns or suicide. Asphyctic child, it's used a lot, and it talks about oxygen, although the translation means no pulse. Okay, watch out for that. And partial pressure of O2, it's dependent on what? It's dependent on temperature and many other factors, but partial pressure of oxygen means nothing else than dissolved oxygen in blood. That's very important. You don't care how much oxygen is bound to hemoglobin. You only care about this. If you would have no hemoglobin in the blood, the partial pressure should be the same, in case the pressure of the oxygen in alveoli and everything else are normal. Okay? And the same accounts for CO2. Okay? But still, there's one more or two more equations I would like to stress out. And one of them is oxygen delivery. And I don't know if someone did the formula with it, but delivery of oxygen means, or you don't have to know so well the exact formula, but you should really remember what are the main factors, on what is delivery dependent. And one of the main things, that means how much oxygen gets to the tissues, let's say in 1 minute. And that's crucial because you want to get the right amount that the cells can live. And the delivery is dependent on cardiac output very much. That's why the beat of the heart and the cardiac output is so crucial. Okay. And every time the cardiac output is decreased, there's going to be decreased delivery of oxygen, of course. Okay. And the formula exactly is like this. 34. So first factor is cardiac output. The other one is hemoglobin. Okay. And hemoglobin is crucial, and we're going to talk about this today and also in the other. Then there is saturation. And then also this part talks about actual dissolved oxygen. Okay. This is a factor times partial pressure of O2. Okay. And what is crucial over here, these two are the most crucial. And of course the partial pressure of oxygen. Saturation is a function of the partial pressure. But if you look at this formula, you should realize two things. First of all, cardiac output is crucial and hemoglobin is crucial. And basically, if we wouldn't have hemoglobin, yeah, we could transport some oxygen into the tissues, but the circulation would have to flow amazingly fast. So the reason why we have hemoglobin is that we're able to bring much bigger cargoes of oxygen with a slow flow of the blood. Okay? And actually the thing you should understand is every time the hemoglobin decreases and you're having anemia, the natural compensation of this is increased pulse. That the heart has to work much more. That's why also all the old patients are at risk because they have many other diseases. They have atherosclerosis. If the hemoglobin goes below 100 grams per liter, then you should really do something with the patient. And the thing you should do is to give a transfusion with old patient. And why? Well, because this person who's like 70 or whatever, his coronary arteries are really narrower, and he's at risk having a MI, okay, and a stroke or whatever you want. But especially the heart is the one which is overloaded because it has to work more if you're having anemia. And this is the typical thing. The people with anemia, old people, they die on MI. So every time if someone comes and he's feeling like dyspneic and whatever, first deal with the anemia in case there it is, okay? Yeah, young person will be fine with anemia 90. So that's why you should really watch out for the older patient, okay? So this is one formula you should really remember. And the other one is the alveolar-arterial gradient. So gradient. And over here it basically tells you what are the differences between the partial pressure of oxygen in the alveolus itself and then when the oxygen gets into the blood. So there's a difference. You know that if you want some molecule to flow from one place to another, it has to be from a place of higher pressure to lower pressure, okay? And remember, another magic number, A gradient normally should be not higher than 10. That means the difference. So for example, if alveolus there is a partial pressure of oxygen 100, then when diffusion goes on and whatever, then in the blood, which gets out of the lungs, there's going to be 95 or 90, okay? Or 95 is normal, so that would be A gradient 5. And every time the gradient is increased over 10, there's a problem with diffusion. Okay? Yeah? There's something wrong with the thickness of the alveolar capillary membrane. It could be thickness or in surface. Okay? Yeah? So A gradient, and there's a special formula you can use, but to be exact, you would need to put something more special, like really sophistically count to know the pressure in alveolus. But you can cheat in a way, and there's a formula which gives you the same thing when you use the partial pressure of CO2. Okay, it's a made-up formula. You're gonna know sort of, not exactly, but it's pretty precise. If you use a arterial partial pressure of CO2 in this formula, you can count how much it is about in alveolus, how much is the pressure. And normally the formula is like, or as I said, normally it's like 100. So times partial pressure of CO2 minus PaO2. Okay? Yeah. So over here you're using arterial, that's you get from blood gases, and you just put it into the formula, and then you can sort of count the A gradient, and normally it should be like 5 till 10. Over 10 is pathology. Increased A gradient is pathology. And this is increased by what? Can you guess? Well, obviously, for example, if you're having pneumonia, because there's inflammation of the alveolar capillary membrane, and it's going to be increased. Or if there is a left heart failure, of course, because it's edematous again, and the membrane is thicker. Okay, or any kind of interstitial fibrosis of the lungs. If the parenchyma gets fibrotic, yeah, you're having that. Okay, and then these are more common things. And as we talked about restrictive diseases, the pulmonary restrictive diseases, those are the interstitial lung processes, and there are thousands of them or hundreds of them, like any kind of autoimmune, SLE, sarcoidosis, pneumoconiosis, any of these will have an increased A gradient. Okay, that's one side. And the other one is, and we're going to talk about it more, but it's, for example, pulmonary embolism, because in this case, again, the blood is not able to go through the lungs well. There is an increased dead space, and that's why you're having increased A gradient. What I mean by that is that in alveoli, the pressure would be nice, normal, but the oxygen is not able to get to the blood fast enough because the surface that is used for the transport or for diffusion is decreased. Okay? That's pulmonary embolism, obviously. And then don't forget what? Right to left shunts. That's very important. Because then blood bypasses the lungs, and thus the partial pressure of oxygen, which is in alveolus, is okay, because there's nothing wrong with that. But if the blood bypasses the lungs, then the partial pressure of oxygen in the blood is decreased, because there's a lot of blood that actually came straight from the veins, in a way to say, and that diluted the oxygenized blood. Okay? Yeah? So again, in this case, it's going to be increased. And on the other hand, you can sort of, with this A gradient, you can also tell in case there's a problem with control of the lungs. So if there is essential control, and the way how you're going to do it is, you see there's hypoxemia in the blood, you count the A gradient, and it's going to be normal. It's going to be less than 10. And this basically tells you one most common thing nowadays, and it's that the ventilation is not proper, the control is not optimal, the patient is hypoventilating, and because if you look at the formula, this will go up because it's hypoventilation, so he's having hypercapnia, and because he's hypoventilating, and he has decreased oxygen. Okay, yeah, but because this is 150 minus bigger number, minus again decrease, sort of it makes it normal, the AA gradient. It's below 10 still. But the patient is hypoxemic. The partial pressure of oxygen in the blood is decreased. And the most common cause you'll see in hospitals is intoxication by opiates. Remember that. Okay? They're intoxicated or something else which decreases their ventilation. So remember that. Okay? Or you can have two other like special cases, and that's when they're going to go high up in the mountains. And there's decreased partial pressure of oxygen. So basically, if there is decreased partial pressure of oxygen in the air, you're going to have also hypoxemia, but with normal AA gradient. Okay? So if it's a fibrotic process in the lungs, AA gradient obviously is going to be increased. But if, especially remember opiates with the hypoventilation. Okay? Yeah? So let's get to the next page. So, thanks for watching, and don't forget to subscribe and ring that bell. And as always, check the description below for supplementary questions and other materials.